So, good morning, everybody. Thanks for the invitation. Today, I would like to present to you Phoenix, which is the first efficient crypto-agile hardware sharing for two post-quantum crypto systems, namely ML-KEM and HQC. In order to give a little bit of introduction, nowadays, one of the major problems in the cybersecurity is the quantum threat, meaning that in the future we will have a powerful quantum computer able to easily break the hard problem on which the current algorithm that used to protect our data rely on. One of the solutions is the utilization of the post-quantum cryptography, which is a new branch of cryptography aimed at designing a new algorithm and based on new hard mathematical problems, which are meant to be secured against classical and quantum attacks. So, in the context of the post-quantum, the National Institute of Standardization and Technology recently selected and standardized two post-quantum algorithms, namely ML-KEM and HQC. And now the problem is how to apply what is called the quantum safe transition, meaning that we have to migrate from pre-quantum algorithm toward the post-quantum. In the context of this transition, there are basically two different approaches that can be used. The first approach is called hybridization, on which we are trying to propose application that take into account both pre-quantum and post-quantum algorithm. While the second approach, it is what is called crypto-agility, and it is what is interesting for today. So crypto-agility means proposing application that takes into account just post-quantum algorithm and possibly using different hard mathematical problem. Why this? Because nowadays we cannot rely at 100% of the maturity of this algorithm, and so it is important to have a different product, different algorithm that we will protect our future data. In the context of this presentation, we will focus on the crypto-agility between the two NIST standards, ML-KEM and HQC. And if we look in the state of the art of this crypto-agility with respect of the hardware implementation, we can see just two implementations. However, if we look inside this work, we can notice that there is not an efficient sharing strategy in order to implement this algorithm efficiently. And so this is the question that we address during my thesis. So the presentation of today is structured as follows. So first of all, I will start by briefly explaining a little bit this crypto system and how it is possible to find some efficient trading strategy. Then I will briefly describe the current state-of-the-art solution in order to perform the polynomial multiplication inside this crypto system. And finally, I will propose our sharing strategy proposal, giving at the end some results. So, first of all, we are talking about two post-quantum crypto systems, namely ML-KEM and HQC, which are based on different cryptographic family, respectively lattice-based and code-based. Between these two crypto systems, they are based on different mathematical problems. And it is interesting to notice that the confidentiality and the security of this problem relies on the introduction of an error in order to make hardware the recovering of the secret key. So, at the first glance, now we can say that the framework seems pretty closed, right? However, if we look inside the internal structure and the internal specification of the algorithm, we can immediately see, for example, how the parameter n, which identified the size of the data to be processed, it's quite different. And also, the polynomial ring instantiation used to process the arithmetic operation are pretty different. So now our question is how to implement this crypto-agility efficiently. So, in order to implement it efficiently, we will try to find some sharing strategy, where the sharing strategy means try to identify some operations that are similar or that are common between the two algorithms. And in order to find them, we will start doing a software profiling in order, first of all, to understand which are the operations that are inside the crypto system, and which are the respective bottleneck. So we can see here that the two main bottleneck rely of the hash function and of the polynomial multiplication. So we can start, based on this operation, try to identify some sharing strategy. We can see that if we try to mutualize the hash function, it's a very straightforward approach, because in both the algorithm, this operation is done using the same FIPS 202 standard, while try to mutualize the polynomial multiplication is difficult, simply because the two techniques using the algorithm are different. So what that we proposed in our work is the introduction of a new technique for performing the polynomial multiplication in HQC, which is called Frobenius additive fast Fourier transform, which not only well suited for our sharing strategy solution, but also try to increase the bottleneck of this operation, which is now implemented using the two-way Karatsuba. At this point, we identifying this sharing strategy, so now we have to understand how to accelerate it. So one of the possible solutions is to use a system-on-chip architecture, where a system-on-chip means the integration of different modules, different systems inside a single integrated circuits. So the elements that compose a system-on-chip are, for example, the microprocessor, which is in charge of executing all the instructions. We also have some memory which keeps the instruction and the data to be processed. Then all the modules inside the system on chip are connected using the system bus, which is in charge of the data exchanging between all the different modules. And finally, we have our application-specific accelerator. For this domain, we can distinguish two different approaches. We call tightly coupled accelerator the blocks that are directly inside the processor, as in this case, and we call loosely coupled accelerator the accelerator that are integrated and that are attached directly on the system bus. So which is our scenario? Our scenario is to propose a sharing hardware block, reported in yellow here, that not only improved the performance of the target operation inside our sharing strategy, but also does the job using less resources in terms of area, with respect of the sum of the singular accelerator for each crypto system. So this is our optimal scenario. So now we will start going into the details about these two sharing strategy solutions. First of all, I will recall how in general it is possible to perform a polynomial multiplication using the fast Fourier transform. So the idea is to start on two data, or in this case on two polynomials, evaluating this polynomial using what is called forward FAFFT, which allow us to change from the canonical basis to the new polynomial basis, apply the pointwise multiplication, and retrieving the final result in the canonical basis by performing the inverse FAFFT steps. So, as it is possible to see, both the forward and the inverse FAFFT are characterized by a regular structure, and the execution of this step are performed using some block, which we call the processing element. In the case of the number theoretic transform, or entity, we have an FAFFT-like operation applied in the context of the finite field. As we can see, for the forward, for the inverse, all the processing elements are characterized by a butterfly structure. And if we go inside this butterfly structure, what that we can find are arithmetic operation in the finite field, where these operations are, for example, the modular addition, subtraction, and the modular integer multiplication. When we talk about the pointwise multiplication, it's a little bit more difficult, since the entity split the input polynomial using an incomplete approach. It means that all the result of the FAFFT step bring us to some data that contains two coefficients. And so in order to perform the pointwise multiplication between each points, it's more difficult. However, we can optimize this operation using the two-way Karatsuba approach. And also for this case, the execution of this technique is done using butterfly structure. So if we look in the state of the art about the Arduino implementation of the entity, what that we can find is a general configurable hardware design which mutualized all the butterfly that we have seen so far, and which implement some atomic arithmetics operators which execute operation in the same polynomial ring. So now we will see the new technique that we propose in order to be integrated in the HQC. So we are talking about the Frobenius additive fast Fourier transform. The concept is similar to the entity. We have an FAFFT-like operation applied in the binary field. What is interesting to notice is that in order to perform this step, we have to recover and we have to compute a new basis, which is called the Cantor basis. And also in this case, for the forward, for the pointwise, for the inverse, we can perform this step using butterfly structure. If another time we go into the detail about this structure, all the operations are performed using binary field, so all the operations follow a carryless approach. And the two most common operations that we can find are the carryless addition and the modular carryless multiplication. So, first of all, what that we did is to implement this Frobenius additive FAFFT operation starting from an existing software implementation in the state of the art. After, what that we did is conducting a profile of this operation in order to understand which are the steps that cause that are the bottleneck of the operation. And as expected are the forward and the inverse FAFFT. And once that we finished the implementation, we integrate the Frobenius in the HQC. And here I report a benchmark that we did. So we integrate this operation for all the three security levels. And as we can see, with respect of the baseline software implementation that used the reference two-way Karatsuba, our proposal leads us to a better performance between 4 and 8 times faster than the state-of-the-art solution. So now we described a little bit this polynomial multiplication strategy, but actually how we can combine these two operations. So we have to address two different questions. First of all, we have seen a lot of butterfly structure belonging to two different techniques, but in practice, how we can mutualize using an hardware approach. So this is the first question. And the second question is actually how we can manage the difference in terms of polynomial rings between these two operations. So to answer the first question, we proposed a structure that is called super butterfly, which not only integrate two entity butterfly rather than one, but also has inside some operator that takes into account the different in terms of mathematical foundation. So inside this structure, we proposed two different hardware design to take into account the difference of the mathematics operation. The first one is called agile modular arithmetics, which takes into account the carryless addition in the Frobenius and the modular addition and the subtraction in the entity. Our idea to address the problem of executing all of these operations are to split the modular execution in two branches. The first one where the result is already in the is represented as a value inside the finite field, and the second branch where we have to insert a further constant which relies of the modulo of the operation in order to get the final result that is in the finite field. To address the carryless addition, we can see that in the second branch we perform this addition between the three inputs using the carry save adder, and the structure of the carry save adder allow us to split the final result into value, so the carry and the sum, where the sum is the sum using the carryless approach. So in order to manage the carryless addition, we can simply propagate this value at the end of the operation. Then we propose an agile modular multiplier, when a modular multiplier means performing first of all a scalar multiplication and then performing the modulo in order to get the final result. Here in this case we managed, we didn't mutualize the modulo due to the fact that the two techniques are completely different, but instead we mutualized the agile multiplier. In order to implement this operation, we proposed an hybrid two-way Karatsuba, where basically the idea of the two-way Karatsuba technique is to split the input value in A and B into alpha, computing some temporary value, which are called Z0, Z1, and Z2, and combine them in order to get the final results. So in this case, in order to compute the carryless multiplication, we can simply use the two-way Karatsuba in the carryless form, while for the entity, what we can do is to transform these two multipliers, M0 and M1, by giving the opportunity to propagate the carry inside. So at the end, we integrate this super butterfly structure inside a more complex loosely coupled accelerator that we will call the Phoenix, where our goal is to do, not only to verify all the functionally configuration of the super butterfly, but also to give the complete overview of the acceleration operation that we want to target. Phoenix is also able to optimize some operation in the ML-KEM crypto system, since our goal is not only to manage a singular polynomial multiplication, but the complete vector times vector polynomial multiplication. So we are in the most interesting part about the result. So first of all, we integrate our solution in a system on chip of the ZIPO Z7 board. So all the system on chip run at a frequency of 125 MHz, and we implement our Phoenix solution using the RTX7 FPGA. Then, in order to compare the impact in terms of resources of Phoenix, we compare our solution with some existing entity hardware work. Why this? Because we noticed that in the current state of the art, there is no any hardware implementation that takes into account the new technique that we used called Frobenius. As we can see from this graph, we can notice that in terms of number of cycles to execute in the entity, our solution is pretty aligned on the state of the art, while in terms of resources, of course, it brings some overhead, which vary between 1.2 and 3.2, and this is actually nowadays the overhead that we estimate for the introduction of the agility. Then we also perform, compute the performance of Phoenix integrated in the two target crypto system. So first of all, for ML-KEM, we integrate Phoenix for all the three security level, and we compare the performance in terms of speed up factor. Why this? Because we are not able to compare our work with the existing state-of-the-art work performing on the same board, and so we try to identify the gain of our proposal in terms of speed up. If comparing our result with the one of the second work on the graph, which is the work of Fritzman, we can see that the speed up factor are aligned, although the Fritzman work used an entity hardware implementation, which is tightly coupled in the system on chip. So, which means that has a lower data exchange overhead. Finally, if we also implement this work with the third work in this graph, which is the work of Wang, we can notice how the work of Wang has a yes. The speed up, yeah, so the speed up is the software implementation with the hardware accelerator inside over just the baseline software implementation. You're welcome. So we can notice that the work of Wang achieve a better performance due to the fact is also integrate some assembly optimization for the FIPS 202 standard, which as we have seen at the beginning of the presentation is one of the main bottleneck of the crypto system. So the story is different for the integration of the HQC, since nowadays there is no work that takes into account the Frobenius, that integrate the Frobenius technique in the HQC. So in order to valorize our work, we estimate the impact of Phoenix inside the HQC with respect of our first contribution, so the HQC with the Frobenius. And in this case, we notice that we are able to speed up the performance between 10 and 14 times for the three Key Encapsulation Mechanism function. After, if we play a little bit of the transformation in the FAFFT domain using this new technique, we are further able to optimize the performance, especially for the encapsulation and for the decapsulation. So to conclude, we understood that the crypto agility is the key nowadays to maintain the security of our future application. And we also understood that proposing efficient sharing strategy is not always straightforward. However, in this work, we propose the first efficient sharing strategy that takes into account the existing operation in the ML-KEM, which is called entity, and a new proposition for the HQC, which not only well mutualized these two target polynomial multiplication strategy, but also gives some improvement in terms of performance. And so, so it means that this work is the first work which prove actually the existence of this sharing strategy. So during the presentation, we have seen some limitation that at CEA-LETI we are trying to target. So the first limitation is that we are actually not able to prove the impact of our sharing strategy, so of our Phoenix, simply because there are not some efficient fast Fourier hardware implementation. And this is one of the points that we are working now. And the second limitation is that we have seen that the performance of the ML-KEM suffer a little bit. So actually they are not very optimistic. However, we identified one of the problems, and so the problem is that on the system bus that we are actually using in order to integrate our solution, and in this period we are also working to optimize this solution. So thank you.